Diamonds tend to grow into cubes at lower temperatures and octahedrons at higher temperatures. Trace amounts of water, silicon, germanium, or magnesium might also influence a diamond's shape. And diamonds never naturally grow into the shapes found in jewelry. Those diamonds have been cut to showcase sparkle and clarity. Environmental conditions can also influence whether crystals form at all. Glass is made of melted quartz sand, but it isn't crystalline. That's because glass cools relatively quickly, and the atoms do not have time to arrange themselves into the ordered structure of a quartz crystal. Instead, the random arrangement of the atoms in the melted glass is locked in upon cooling. Many crystals don't form geometric shapes because they grow in extremely close quarters with other crystals. Rocks like granite are full of crystals, but none have recognizable shapes. As magma cools and solidifies, many minerals within it crystallize at the same time and quickly run out of space. And certain crystals, like turquoise, don't grow into any discernible geometric shape in most environmental conditions, even given adequate space. Every crystal's atomic structure has unique properties, and while these properties may not have any bearing on human emotional needs, they do have powerful applications in materials science and medicine. Have you ever wondered why you can see through glass, or what fire is made of? Did you know gold doesn't originally come from our planet? Find out more about the fascinating makeup of our environment with this playlist.
Geology. I'm Andrew Dunning, and this is the Alvord Desert. The Alvord Desert is Oregon's largest dry lake bed. It's over 20 kilometers north to south and 10 kilometers wide. Because of the lack of topography on this flat lake bed, the winds rip across here at record speeds. It's formed by the rain shadow created by Steens Mountain. Steens Mountain is one of the largest fault block mountains in North America. It's over 5,000 feet from the top to the lake bed here. So as one of the more unusual features of Oregon, Steens Mountain and the Alvord Desert have been a hub for geologists going back over 100 years. So how did we get here with an enormous faulted mountain and a flat lake bed? The story goes back about 20 million years when the Alvord Creek Formation and the Pike Creek volcanics were the first eruptive volcanic rocks to reach the surface here. These volcanic rocks form the base of Steens Mountain over here, though even older rocks dating back to the Triassic are exposed further to the south in the Pueblo Mountains. The most common rock formation around here is the Steens Basalt. Now, the Steens Basalt are the earliest members of the Columbia River Basalt Formation. Now, the Columbia River basalts were an enormous outpouring of basaltic lava that came from vents that started around here in Steens Mountain and stretched all the way up into Washington. Several hundred kilometers of these dikes and eruptions that blanketed the Northwest in lava. So around here, the Steens basalts are about 2 kilometers thick, which is an enormous volume of lava. And many earlier geologists interpreted Steens Mountain as a sort of shield volcano, but now we know that there is significantly more folding than there is actual piling of lava into a volcano shape. The enormous vertical relief of Steens Mountain's east side is due to the Steens Fault, which runs a tremendous distance north to south and includes many other substructures. The Alvord Desert is within a graben, which is bounded impacted by faults on both sides and has dropped down. The flat rocks on the east side of the Alvord Desert and the rocks on the summit of Steens Mountain are the same rocks. So this shows just how much vertical offset there has been. There's over 3,000 meters of vertical offset across the Steens Fault, and this fault has been active for about 10 million years. We know that because the Pike Creek and Alvord Creek volcanics didn't cool down until about that time. And we can use that as a proxy for how long this fault has been active. More recently, the Alvord Desert was host to a large lake. During previous ice ages, the Alvord Desert was home to a large lake, about 60 meters deep. And this lake cut terraces and wave-cut benches all around the perimeter. So this uplift in this valley that these faults have created is part of the Basin and Range, which is an enormous tectonic province that stretches from here in Oregon all the way south to Mexico. And the fault histories and uplift histories we've been able to construct from the rocks right here have shown that these faults were part of the earliest onset of Basin and Range extension in Oregon. This Steens Fault is still active, and based on several trench sites near the Alvord Hot Springs, we have determined that the last earthquake occurred about 8,000 years ago. There are three main hot springs found in the Alvord Desert area: Mickey Hot Springs to the north, Alvord Hot Springs in the center, and Borax Lake down to the south. Mickey Hot Springs has water seeps over 90 degrees Celsius, and the Alvord Hot Springs is over 70 degrees Celsius. This tells us that there's a high heat flow moving up from deep within the earth and heating up shallow groundwater. Where is it coming from and why is it doing this? Well, we're not entirely sure, but the magnitude and size of the Steens Mountain Fault probably shows that this is a very large and deep structure that extends far into the earth and allows fluids to rise. These fluids are also responsible for altering the Pike Creek volcanics and the Alvord Formation. I'm up here at Pike Creek now, which is one of the major drainages draining the east face of Steens Mountain. You can see the face of Steens Mountain behind me in the canyon. Up here at Pike Creek, we can see several different volcanic episodes that shaped the evolution of this area. What the rocks we're standing on now is called the Pike Creek Volcanics, and this is mostly rhyolitic lavas with some welded tuffs and other sedimentary rocks like lakebed deposits. And these indicate an environment, a volcanic environment, that existed before the Steens Mountain flood basalts were formed. So we had highly evolved magmas here, these rhyolites, which are very high in silica, erupting before the bathic and primitive Steens Mountain basalts flowed out across the landscape. These Pike Creek volcanics are interesting in another way in that they contain uranium. Back in the 1950s, there were a number of uranium prospects and mines in this area, including in Pike Creek, though no significant production ever came of this area. The reason we have heavy metals like uranium in these rocks is because this fault system that uplifted Steens Mountain and these Pike Creek volcanics is very deeply rooted, which allows fluids, water laden with minerals, to rise up from deep within the earth. And faults that formed within these volcanic rocks concentrated these minerals, like uranium, in a way that was